Okay, we're at I think section 14.3 pressure measurements. Um, so let's share the screen here, and one of the methods for measuring pressure is a barometer, now developed by Torricelli. As a matter of fact, in some of the labs I used to work at, we measured uh, pressure in torr. Atmospheric pressure was 760 millimeters, 760 torr, um, and we'll see that as we uh, make some calculations here. So the you have here it's mercury, and it you have this column of mercury. You start with this tube. You pretty much evacuate the tube and insert mercury in, put it in this mercury bath. Of course, mercury can be very dangerous, so you don't find these much anymore. Um, but you can see at the top of the tube, P equals 0. It's pretty much a vacuum. It's pretty close to a vacuum, and so the atmosphere pushes down on the open part where you see the P0 at B. A and B are at the same pressure. If not, there would be flow. If they weren't of equal pressure, there would be flow. But since there is no flow, A and B are at the same pressure. So the pressure of the atmosphere on the mercury bath is the same as the pressure, P0, which is the uh, density of mercury times g, the gravitational acceleration, times the height of the mercury. So uh, h, it gives you the height is a measurement uh, that we get. It's the atmospheric pressure is a 1.013 times 10 to the fifth Pascal times divided by the density of mercury, which is 13.6 times 10 to the third kilograms per cubic meter, times 9.8 meters per second squared. And if you calculate that out, you get 0.76 meters, 760 millimeters. And that's how some people reported 760 millimeters of mercury. Now, you're not used to hearing that on the news. You don't hear anybody talk about 0.76 meters or 76 millimeters. They talk in inches. It's inches of mercury. And if you do the conversion of 0.76 divided by 0.0254 millimeters or 0.0254 meters per inch, you get 29.9 inches. And that's probably what you're more used to hearing on the weather forecast is if there's a storm system and the pressure dips, you'll hear um, 28 inches of mercury. So here in our weather forecast, where it's expressed in inches of mercury. So here's one way of measuring um, pressure. Here's another way. Uh, you have this pressure in this bulb here, and you have a fluid that uh, is in this open tube, and P0 is the atmospheric pressure. So again the um, the the pressure is the uh, P0 plus rho GH, whatever the material is. Now, if you subtract P from P0 and all you get is the rho GH, then you're measuring gauge pressure. And so when you're and basically you're subtracting the atmospheric pressure from the total pressure. Um, is, the absolute pressure, what they call the absolute pressure. The absolute pressure is the atmospheric pressure plus the rho gh, um, and the so if you subtract the atmospheric pressure, uh, you get what is called gauge pressure. So when you put your little gauge to the tire, you get in how much pressure is in the tire itself without taking into consideration the atmospheric pressure. So that's the absolute pressure is the P, which is atmospheric pressure plus rho gh. and the gauge pressure is just the rho GH. So let's do a little quick quiz here. And several common barometers are built with a variety of fluids. For which of the following fluids will the column of fluid in the barometer be the highest? Be the highest: mercury, water, ethyl alcohol, and benzene. Which of these would be the highest? Well, unless you committed the table that was given up above to memory, you won't get this answer. And so I cheat. I give I'll give you the densities of these different materials. Mercury is 13.6 times 10 to the third kilograms per cubic meter. Water is 1,000 kilograms per cubic meter. Ethyl alcohol is 806 kilograms per cubic meter, and benzene is 879 kilograms per cubic meter. Well, it would be the lightest of these would have the tallest, would have the column would be the tallest. It would be the highest. So the lowest of these is which? Ethyl alcohol. And there's the answer there, ethyl alcohol. So that's it. Next we'll go with buoyant forces and Archimedes' principle.